Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell, and in today's episode we are joined by a special guest, Ahsan Zaman, and he is from Silanna Semiconductor. So, thank you for being here today, and my first question to you is to basically tell us who you are, what you do, and why it is you do it.
Thanks, Robin. Thanks for having me. So I'm Ahsan Zaman. I'm the Director of Product Marketing at Silanna Semiconductor. I am responsible for AC to DC line of products that includes our flyback and active clamp flyback controllers. And one of the challenges or one of the reasons why I'm doing this, because this is a very exciting field where the dynamics of the market is always evolving. There is a lot of new demand for higher power density and high efficiency power adapters and power supplies. So it's a really exciting field to be in, where there is a constant innovation and drive for improving efficiency and on the broader spectrum of things that really helps coming up with a more greener solution that helps ultimately the environment and more efficient power management solutions.
Fantastic. Now, you're on the podcast here today to talk about some stuff that relate to your company. Specifically, I believe it's to do with GaN and silicon power FET solutions. So, could you give us a bit of an introduction as to what these solutions are and why they're important?
Sure, yeah, absolutely. So, our company really focuses on designing active clamp flyback controllers, which are going into a wide variety of applications, including power supplies for portable electronic devices. So that means these are power adapters and battery chargers that we use on our everyday life to charge our laptop, cell phones, tablets. And one of the key challenges there is always the market wants to design power supplies with much smaller size so that it's easier to carry. As the power supply is required to be more smaller and higher power density, the key challenge is always how do you make them more efficient at the same time, because the efficiency and the size, they go hand in hand. So if you really would like to improve the power density, you always have to improve the power efficiency. Otherwise, you have the same heat being trapped in a smaller volume and increasing the temperature of that adapter. So now we designed a controller. That means like our controller is technology agnostic in terms of what external FET or external MOSFET being used or being interfaced with. We have shown that our controller is almost equally as effective pairing with silicon FET, which is considered as a lower cost solution. And often in many power supplies, they are provide sufficiently high efficiency, whereas the GaN, the gallium nitride devices, are considered more of an exotic semiconductor device. They have a recent trend of becoming more and more popular, and they started being widely adopted in high density, high efficiency power supplies. And we have also come up with reference designs and come up with customer designs where our controllers being interfaced with GaN FETs, where we are able to deliver higher efficiency with slightly higher cost. So on both in terms of semiconductor technology, silicon has been around for a longer period of time, so people are more familiar with the FET. The cost of economics has also been scaled down over the years and in high volume production, versus GaN being a newer entry to this field has been looked at a little bit more expensive alternative. However, they have a better figure of merit that provides slightly better efficiency and performance. And what we have really shown in Silanna Semiconductor, that our controllers being technology agnostic can be easily paired with either or depending on the customer's need. And do they really need the best performance versus they want to optimize it for lower cost while still keeping reasonably high performance.
Interesting. So to be clear, it's not that your company produces GaN or silicon power FETs, but you're producing the controllers that you use with those power devices.
Correct. So our company is focused on developing controllers, and one of the key differentiations or one of our highlighted product has been fully integrated active clamp flyback controller. So fully integrated meaning all the active clamp circuitry has been already integrated into the controller. So the active clamp flyback controller has been around for several years or for quite some time. However, their challenge has always been with additional circuit, you need to have additional driver, you need to have additional FET for the active clamp. Although they provide better performance, they provide additional loss reduction mechanisms such as uh, recycling of the leakage energy, and they provide additional benefit in terms of EMI, reducing switching losses, but they are often considered also more complex, or you need more additional circuits to complete the system. However, with our controller, the problem that we have really solved is coming up with a fully integrated active clamp flyback controller, and the integration part meaning all that active clamp circuit, that means the driver, the FET, has already been integrated in our controller. So for the end user perspective, this looks like a very simple controller to design your power supply with, and it still provides all the benefit of the active clamp flyback controller, things that I have already mentioned, better efficiency, lower thermal dissipation, and much better EMI and lower switching losses. However, the design is still kept very simple so that the customers don't need to worry about the additional circuitry. All of that we have taken into within our controller IC. So it's a single package device that integrates the controller as well as all the active clamp circuitry.
Now, it's quite interesting how you're saying that the controller solutions that you provide essentially reduce the number of external components that you need to power the larger FET and GAN devices. And going back to an earlier point which you made about thermal dissipation, I take it that not only is having an all-in-one controller helping reduce the number of external components, but I also imagine it helps in terms of heat dissipation because of the fact that you haven't got so many external components getting in the way of heat sinks and thermal removing systems like that.
Absolutely. It helps with both reduction of the external components as well as those thermal dissipating or thermal management components such as heat sink, as well as like additional thermal paste you may need to apply for. And that helps both in terms of cost reduction as well as reducing the weight of the power supplies, because some of those heat sinks, as you can imagine, they are quite bulky and heavy. So by improving the efficiency, you are allowing reduction of the cost, you're allowing reduction of the component that affects with the cost and the weight of the device, and ultimately making them more smaller.
Now, the weight of the device, that's an interesting one, because I know for a fact that certain technologies like silicon carbide are being looked at in terms of EVs. And so I can imagine that if you're able to reduce the weight of the controller stage and therefore reduce the weight of the whole thing, the efficiency of an EV also goes up.
Correct. Yes. Silicon carbide is also another FET technology, which has also been looked at more recently in the like low to medium power, like from less than 100 watt to few hundred watt power supply. Although like in the past they have only been looked at for much higher power applications like inverters and EV chargers. But yes, basically that improving the efficiency to ultimately reducing the size and the cost is what our controller provides. And whether it's a silicon carbide device or a GaN device or it's just a silicon device, it ultimately brings in all those benefits in its within that figure of merit of that device. It enhances the best performance, or it squeezes out the best performance you can achieve from any given device.
Now, in terms of the controller itself, you mentioned multiple different types of technologies, in terms of power FETs and stuff. Is it that one controller can handle all the different technologies, or that you need different controllers for different technologies?
Yes. It's a one controller, and as I mentioned, we designed this controller to be technology agnostic, so that the customer ultimately, based on their performance need and their cost appetite, they can decide what is the best or the most ideal FET technology to be paired with. And given like all the FETs have slightly different parameters, things such as like the gate drive voltages, you may sometimes need to add like a few additional components to interface that FET with our controller. But that's like very easy to do, and regardless of what type of FET technology you're using, the benefit of the controller, that active clamp flyback operation, clearly demonstrates against more conventionally used flyback controllers, such as like there are QR quasi-resonant flyback controller or RCD snubber-based flyback controller, where you have like inherent losses coming out of the leakage inductance as well as the diode, resistor, and capacitor losses. That part of the loss we completely eliminate through recycling that energy. So that benefit of the active clamp flyback controller still holds, regardless of which FET technology you're using and how you may need to kind of adjust the gate driver to interface with our controller.
Now, your controller, I imagine, is it powered by a microcontroller in terms of being able to be? Is it programmable essentially?
No. So this is so we have a digital controller, which is the brain of our controller. So it is implemented as a ASIC. So it's not a microcontroller. It doesn't need to be fully configurable from the customer's point of view. But the controller itself is very smart. We have included a lot of intelligence so that the controller can detect what operating conditions you're operating at. It can detect certain things about the environment, such as the input-output voltages, temperature, current, power level. And with all that information, the controller is always able to guarantee that we are selecting the right mode of operation to maximize the system efficiency, the end-to-end system efficiency. So the controller is built in with that intelligence where it is always monitoring we call it several contact points. So it is sensing all the vital node of a power supply. And based on that, it's making a very well-informed decision to figure out what should be the mode of operation. For example, when you are at a very light load, like a lot of the power supplies, and you would agree, spend most of their time doing nothing. They are just plugged into the wall. We just charge our phone maybe a couple of hours every day, and then I take my phone away, but the charger is still left plugged into the wall. So that means that is like a standby mode or an idle mode. So our controller is able to detect when it is in the idle mode, and it really reduces all the power consumptions of the system to maintain a very low current operation mode so that the standby power is practically very close to zero. So it's not consuming nothing when you're plugged into the wall. Versus when you plug in your phone, depending on what your instead of the charge of the battery, if your phone is plugged in with 10% charge only, obviously it starts to drain a lot of power because it needs to quickly charge from 10% to at least like 30, 40, 50%, so that the battery is now well above use limit. And that's when the controller detects like now it needs to provide a very high current to charge the battery, bring it up to the 50% or 60% level, and it goes to a high power mode. And there the goal is to deliver the maximum power while maintaining very high efficiency. Versus once the battery is charged above that 50 or 60% level, then it becomes slower and slower charging, and then the controller starts to detect like now the power requirement is not that high, and it optimizes it to operate with more with more intelligent decisions on how to optimize the power consumption as well as maintaining that steady charge of the battery. So it is built in with that sort of decision making as a digital control integrated in our controllers, and it doesn't require any like custom programming or interference from the user to make those decisions. It's intelligent enough to take care of that by itself.
So that's really quite interesting. That's really interesting, because I've seen other competitor products where they have a programmable microcontroller, but keep in mind the actual controller itself is a rather large board with lots of components on it, and it requires you to connect to a computer to trim and sort of like design the rising, the fall times, all that kind of stuff. But it sounds like what you're saying is that essentially your chip is intelligent enough to actually look at the situation and make its own decisions without needing any user input whatsoever.
Yeah. I mean, for most power adapters that is being used in portable applications, they tend to have very limited configurability from the end user. So, for example, the power adapter that you use to charge your laptop or the one that you use to charge your phone, and these days there is also USB-C, which allows you to use the same power adapter to charge multiple devices. So in most of these cases, it really doesn't require much of interference from the end user. And this is true for us as well as for many of our competitors as well. But in some applications, like especially in higher power applications like EV charging, and in those cases, there may still require like some additional configuration setup by the users. But for this sort of like the power level I'm really talking about, or our products are really targeted for today, is between 65 watt to 150 watt power adapter. That includes like fast charging, all the fast charging power adapters for pretty much all the portable electronic devices. And moving forward in the next year or in the following year, we'll be coming up with higher power solutions, like our same ACF technology can be taken to higher power applications all the way up to like 250 or 300 watt. And the goal there is still being able to deliver the highest or best in class efficiency while maintaining our leadership in power density, highest power density solutions, as well as reducing the number of components so that it becomes a more and more easy to design with system, as well as becomes more cost competitive solution. So we have been working towards taking our technology to higher power, and as things move forward, you will see like our solutions being adopted in higher power applications as well. But today we are mainly focusing on 65 watt all the way up to 150 watt power adapters, and those are like portable.
And just to be clear, this is a one-chip solution.
This is a one-chip solution in terms of the primary side. So in the power supplies, you usually have a primary side, which is the side that gets plugged into the wall or the AC grid. And on the secondary side, you have like additional things such as like USB PD controller. So those chips are still there on the secondary side. But yes, on the primary side, we have a single controller that does this active clamp flyback operation.
That's absolutely fantastic. That's really quite brilliant, actually. And I suppose the one of the major advantages of using an ASIC as well, I suppose it helps to reduce system costs as well on the chip itself, not just the reduction of the external components.
Correct. So yeah, like we believe like if you have no limit in terms of how much money you are going to spend, you can really get the highest efficiency ever, or you can really get the smallest size or highest power density. However, that solution is not going to be a practical solution because the cost will become prohibitive, right? So yes, that's why our goal is not to do like integration just for the sake of integration, but where the value is being added. And our whole concept of doing a fully integrated active clamp flyback controller is really based on that. Like while we are doing this, we want to make sure that we are also optimizing the cost, both for ourselves as well as for the end customer.
Now, I've got another question about this, about the SEDS 1131 chip, and I'm a bit curious about this because you talked about how it's able to make quite a few decisions on its own, depending on what it needs to operate at as it's being used. But in terms of selection of device, is there like an external pin which you use to determine, which you set if you're using a GAN or a silicon FET? Or does it just entirely determine that type of technology by itself?
No, so for that, yes, you will need some configuration selection, correct? Yeah. So we provide some flexibility, especially things such as like, what type of FET you are using, as well as like additional like some programmability. Yeah, that's needed because our controller, we see that being adopted in a very wide range of applications, and there is some sort of programmability is needed depending on the application and their target need.
And one sort of potential sort of solution I can imagine in my head is I can kind of imagine the controller with a few sort of like 0 ohm resistor links. And let's suppose that you've designed sort of like a generic power module, but maybe let's say one of your suppliers for GAN devices has basically gone under and you can't get any more, like we did during the COVID pandemic. You could then swap it out for a different type of technology and just change one of the resistor links, and then that chip would be able to essentially reconfigure itself for that device. Would that be a practical solution?
Yep. So we have exactly like we have a rconfig pin on our IC, so that's the register for configuration, and that basically allows us playing with several parameters that helps with configuring our controller. for various applications and power level and what type of get driver is selected to drive certain type of FET. And that also like I said, like from 65 watt to 150 watt, that's a pretty wide range. And in a power FET that is being used at 65 watt would typically be a higher RDS on or lower gate capacitance device versus a FET that is targeted for higher power. You really want to pick something that has the lowest RDS on, but then unfortunately that comes with a slightly bigger capacitance. So now if you want to use the same controller for 65 watt versus 150 watt, you need to have that sort of configurability so that you can drive both type of FETs with equal efficiency. So yeah, absolutely. So we have a register based configuration scheme that pretty much does the same thing as you mentioned.
Now, when it comes to using these controllers from an engineer's point of view, what would you say is the biggest challenge that engineers face when trying to integrate controllers for power transistors?
Well, the biggest challenge has always been what is your most critical mode of operation and how do you optimize the system for that. And for example, depending on which part of the world you have been, you can get access to 115 volt AC voltage, things such as in North America, or if you go to Asia, then you have 240 volt AC. So there is a low line operation versus high line operation, and all these power adapters are designed to support universal input. So that means the same power adapter that I use to charge my phone, I expect it to work both when I'm in North America versus when I'm traveling in Asia. I don't want to carry a different adapter. I want to use the same charger or adapter to charge my device. So now that means it needs to support a wide input range. And then on the output side, also with the adoption of USB-C, the challenge is now people want to use the same power adapter to charge their phone as well as laptop and tablet and many other portable devices. And depending on which device you charge, because devices have different sizes of the batteries, they could be charged at different voltages. So there is a wide range of input voltages, there is a wide range of output voltages, and that becomes really challenging to ensure the best efficiency or highest efficiency to be maintained over this wide range of variations. So for the designers, it's always challenging, like how do you design a power supply that can not only maintain very high efficiency across this wide range of operation, but also in critical modes, such as when the line voltage is low and you have to provide the maximum power, you want to ensure that thermally the design is viable. Like you cannot really come up with any size of a power supply and expect it to work unless you can guarantee the minimum efficiency is going to be high enough to support that power density. So the challenge has always been the market or the customers always ask for smaller and smaller power adapters. The power density needs to be increased. And how do you really optimize your system to improve the efficiency to support that power density? And that what adds to that challenge is also there is a demand for higher power. As the power goes higher, even with the same efficiency, your losses will also be higher, and the thermal dissipation will be higher. So that really the efficiency and the power density, those two has always been the key challenge for the designers. And that's why our controller really tries to bridge the gap that, yes, we can deliver you higher power density, but look, we also have a supporting proof that our efficiencies are going to be higher to make that solution feasible. So that's where our technology really comes in to help the designers coming up with practical solutions that are viable both commercially as well as like from the technical point of view.
That's actually an interesting point, which you mentioned about a couple of minutes back. You said about, and it's funny how USB used to be just a bus protocol for transmitting data, and then eventually people realized you could charge small devices, and then suddenly people were having very big batteries in phones, big batteries in laptops. You have your Apple Macs and stuff, and then they're all charging over USB, but they need like 80 to 100 watts, not the 10 watts that USB was originally supposed to provide. And it's interesting how by moving everything over to USB, it's a bit of a double-edged sword, because it's great that everyone uses the same cable, but now suddenly you've got a charger that needs to work with 5 different devices, all at different powers. And as we all know, creating a 10-watt charger can be made very efficiently, but trying to make the same 10-watt charger operate efficiently at 100 watts while also providing the same efficiency at 10 watts is almost next to impossible at times. And so that's actually a really interesting concept, which I never thought about, especially when it comes to USB. So that's a bit of an eye-opener.
And I mean,
so
it's about the
go on.
I mean, it's not the challenge is not to maintain the same efficiency. The challenge is actually you have to improve the efficiency. So a 10-watt charger. So let's take a 10-watt charger. If that charger has 90% efficiency, that means you are just going to have 1 watt of loss. So which could be manageable. But now if you have a 100-watt charger, that 90% efficiency would mean you have 10 watt of losses, right? So now the loss is like 10 times. So that means your efficiency now needs to be improved by from 90% to 99% if you want to maintain 1 watt of losses. And going from 90 to 99% efficiency actually means 90% reduction of the losses, because your losses used to be 10%, but now you want loss to be only 1%. So that huge reduction in the losses to benefit the efficiency is the challenge. So as you move to the higher power, that's why you see, like, as you move to the higher power, your power adapter starts to look bulkier and bigger and almost like a brick. A 250 watt power adapter that is used for things such as like gaming laptop or high performance PCs is almost like a brick, very heavy and bulky and big to carry with. And that's mainly the reason, because with a bigger size, you now have a more surface area to dissipate a wider surface to dissipate a larger power. However, the challenge is now, if you want to design a high power adapter with a smaller size, how do you improve the efficiency or really reduce the losses? And that's why our controller is kind of helping with coming up with a more sophisticated or more advanced technology to deliver power from input to output with a significantly improved efficiency.
And so you're not just so that means if you want to make future power supplies that are smaller and more efficient, it's not a case of just making it smaller, because if you haven't improved the efficiency, it's just going to get hotter. Because as you say, the amount of energy it's just going to get hotter, and you've got to try and get rid of that heat, and that's going to become a problem if something breaks in that thermal management system. And so you haven't just got to make it smaller, you've got to make it more efficient, and you've got to make it operate at a wider range of voltages. And so it's not one problem that engineers are trying to face, it's 3 problems simultaneously. So it's funny how, and I think it would be fair to say that in the past, power electronics it's never been really a sexy area of engineering. It's never really been something that a lot of engineers have been interested in, but it's probably one of the most important, especially the way we see these portable devices like mobile phones and laptops being able to consume hundreds of watts of charging power over a tiny USB-C cable. It's absolutely fascinating, actually, that it's become such a crucial area of engineering. But a question which I have now, going back to the products which you offer, these the to be specific, the SZ1131. Why is it that, because you were talking about the active clamp flyback offerings in that chip, but why is it that would be better for future technologies like gallium GaN devices?
So there are several reasons why an active clamp flyback controller is a better fitting device or better fitting controller for gallium nitride devices. One of the reasons is, with active clamp flyback controller, you improve your switching waveform. So every time the device switches, without active clamp flyback operation, you get a very large voltage overshoot. So for a conventional flyback controller, that voltage overshoot or voltage spike would be very close to the voltage rating of the GaN devices. The gallium nitride devices are typically rated for 650 volt to 700 volts, and they are not avalanche rated. So that means if your controller is not able to limit how much voltage they get exposed to, you can cause damage to the device. Even if it doesn't happen instantaneously, over the lifetime, it can get really affecting the lifetime of the GaN devices. Versus the active clamp flyback controller, you really don't get any overshoot on the primary side due to the very soft nature of the switching pattern, and that helps giving you a significant margin from that absolute maximum voltage rating of the GaN devices. So if it's a 650 volt device, what we have been shown that with our controller, even the worst case operating conditions you can imagine. That means highest input voltage, highest output voltage. We can really limit that voltage within like 550 volts. We give like 100-volt margin from that apps max voltage rating of the GAN devices. Versus if it's a QR controller, you just have an uncontrolled voltage spike, and that depends on the leakage inductance. That depends on a lot of like parameters that you really don't have a very tight control on the production, and that would mean like you would get more and more devices failure over the lifetime of those power supplies.
So would it be fair to say that GAN technologies are more complicated to drive than your typical silicon FET?
They're not necessarily more complicated to drive, because the FET operation has been proven like practically as reliable as silicon, but they have more limitations in terms of like certain parameters, such as the voltage overshoots. That's one of the things, as well as like they require some additional like you have to pay attention to how you drive them. Any parasitic inductances or any parasitic parameters in the circuit that goes between your controller and the GAN device may cause additional ringing. They are more prone to kind of getting damaged in that ringing. But there is a very well-defined, established guideline on how to design power supplies with GAN. And mainly, as long as you're paying attention to their design note, you get a good handle of them. You basically make sure they're always being operated in their safe operating limit.
And so engineers who move over to controllers like the ones that you offer will basically find their lives much easier when it comes to designing new power circuits, because they don't have to worry about the controlling aspect of that device. They can just continue to use it as if they were using previous silicon devices. It doesn't matter, because your controller is going to handle most of the hard work for you. And so engineers can deploy these technologies sooner and quicker as well.
Yes, correct. So we provide, in addition to our controller, we also provide like a more comprehensive design guidelines. We also have a design tool on our website called Power Density Hero, which provides for any customer designs, for whether it's a custom design or a more generic design. Our design tool really provides a full list of bill of material as well as the circuit schematic. So yes, in addition to our controllers being smart or to able to be much easier to interface with the GAN devices, we also provide a very useful tool in the form of design tool. Is called Power Density Hero, that helps our customers to design their power supplies.
Absolutely fantastic. Well, I just have one more question for you before we end this podcast. For the engineers who are watching this video, if they wanted to get involved with Silanna Semiconductor and their products and offerings, what would you recommend that they do?
So best is to get in touch with us through our website. We actually provide a really long list of reference designs on our website. And Silanna Semiconductor is not only based on AC to DC controller. We also have a lot of exciting DC to DC controller products. And this is something that's very useful for things such as like multi-port power adapters. So these days, if you go to Best Buy or if you go to Amazon and buy a power adapter, most likely you will buy a power adapter that has more than one port, so that while you are charging your laptop, you can also charge your smartwatch or your phone. And that type of power adapter requires like having DC to DC controllers on the secondary side. So we have a wide range of product that offering, as well as like our website shows like the design tool on how to put together a system using our AC to DC and DC to DC controllers together. And we call it like we are basically provider of end-to-end power management solutions. So starting from the AC wall input all the way to your device output port, we provide the complete solutions. And also we are going to be available, our products are going to be also available through Mouser in the coming weeks. So if you'd like to sample our parts, if you'd like to sample our reference designs, always get in touch with us or one of our distributors, and we'd be happy to help you with your design.
And you heard it first here, Mouser. So check them out. Well, all I can say is thank you ever so much for taking the time to be here on our podcast today.